We've been working hard on DLSS for 3 years now, and today I want to give you an update on how DLSS delivers the best image quality and how the AI in DLSS just keeps getting smarter. DLSS stands for Deep Learning Supersampling, and it's a technology that uses AI to render your video games faster and more beautifully. For every frame of the video game you play, DLSS is running a neural network to reconstruct all of the detail and all of the beauty of the game, but at a much faster frame rate. DLSS is now in over 100 games and applications, and adoption keeps accelerating. We've released integrations for the major engines like Unity and Unreal, and that makes it very easy for developers to integrate. Recently, we released DLSS 2.3, which makes even smarter use of motion vectors from a game in order to improve object detail in motion, particle reconstruction, and temporal stability. In this example, you can see how these particles are being rendered individually without streaking. Here, you can see more of fire ember particles without ghosting. In this example, you can see how this object is much more stable with less flickering. Now let me tell you about how DLSS works and why we built it the way we did. Before DLSS, there was spatial upscaling. Spatial upscaling has been around for a long time. In fact, your television can do it, and it's a pretty common option in a lot of games. Games have in-game resolution scaling, bilinear interpolation, bicubic interpolation, Lanczos interpolation, FSR, and we've offered a scaling and sharpening option in our game-ready driver for some time now that works on all GPUs without any game integration at all. But spatial upscalers come with limitations. They work frame by frame, treating each frame as a separate image and then adding more pixels. They can add more pixels this way, but they can't add more detail, and so the results are often blurry, and they often have more temporal artifacts such as flickering and crawling. DLSS is a temporal method, and it uses information from multiple frames to provide increased detail with less flickering. If nothing is moving, it's easy to use information from multiple frames because you can just stack the frames together and get more detail. But of course, when you're playing a game, things are moving and the appearance is changing, lighting and shadows. It's not so straightforward. DLSS combines AI with geometric motion vectors to make smarter decisions about what information we can reuse from prior frames. Take a look at this example from Control. On the left is the input to DLSS. It's very low resolution and aliased. And on the right is the output from the algorithm with lots of detail and temporal stability. Here's an example of the power of DLSS versus spatial upscaling. This is DLSS in performance mode compared to spatial upscaling in ultra quality mode. The spatial upscaler is running at 77% of the resolution, which means that for every 1 pixel input, it's producing 1.7 pixels of output. On the right, we have DLSS running at 50%, meaning that for every 1 pixel given to DLSS, the algorithm must produce 4 pixels of output. DLSS does more than twice the work and gets a better result. That's the power of AI and temporal methods. Spatial upscaling methods often introduce temporal artifacts. I know that sounds confusing, but the reason for that is that spatial upscalers don't understand how frames are related to each other in time. They have to make a guess for every frame independently. They're not able to track objects over multiple frames, which means when you watch the output from a spatial upscaler, things are going to twinkle, be unstable, and sometimes just be missing. Spatial upscaling methods try to compensate for the lack of detail with increased sharpening. Sharpening can make an image more punchy, but if you do it too much, you get ringing and haloing around the edges of objects. In this example, we see how the sharpening in a spatial upscaling method is really struggling with fine lines. There's just not enough information in the input to the sharpener for it to approximate the lines that the game is actually trying to draw. DLSS, in contrast, doesn't suffer from this because it doesn't rely on sharpening to add detail. Instead, it reconstructs it using temporal methods and artificial intelligence. If you want the output of your DLSS rendering to be sharper, you can use our built-in sharpener or the one from the game. DLSS sometimes provides even higher detail than native rendering because every frame is giving us different sets of samples about how things should look, and we're able to intelligently combine them to come up with a more complete and accurate picture of the rendering. We've made huge progress over the past 3 years to make DLSS more beautiful and more detailed, and the network just keeps learning. The future of AI for real-time graphics is just beginning.